Good morning, students. So in the last class we discussed the electric field intensity due to a infinite length of thin conducting wire. So next we will go to the another application of Gauss law, that is electric field intensity due to a charged infinite conducting cylinder. Before going to this, I want to tell you that here we use the terms conductor and non-conducting. So what is conducting body, another one is what is non-conducting body. The differences if you know, then we go for the applications. First one, conducting body. If you take the conducting body, so conducting means, you know, conductors are nothing but the best conductors are metals. Like metallic body, if you taken, example is metals. So in this, whenever a charge is provided for the metallic body, the entire charge will be resides over the surface of the body only. Why it will happen, that we will discuss it. Suppose if the charge is present, if the charge is present inside, means electric field will be present inside. Why? Because electric field intensity is nothing but E equal to 1 upon 4 pi epsilon naught Q by R square. If Q is 0, electric field is also be 0. So the electric field inside the conducting body is 0. So electric field inside the conducting body should be 0, means charge should not be present inside the conducting body. So why should be 0? Just we will be discuss it. If you assume if charges are present inside it, let us assume that if the charges are present inside, then what will happen? Here, if you concentrate this charge will produce an electric field around it, radially outwards. So at this point, so due to this charge here, at this point P, you know the electric field intensity is away from it. So the electric field produces by this charge radially in all the directions. Then in that electric field the another charge is present. Then this charge will be experience a force. What is the force? That is F is equals to EQ, and the force direction is along the direction of electric field intensity. So the force will be act F equal to EQ in this direction. Then what will happen? This charge will tends to move along the direction of force. If the charge tends to move in the sense they will produces the current. But what electrostatics? Electrostatics in the beginning we discussed. Electrostatic means the study of charges which are at its static position, means the charges should be at rest. But here charges are in motion, so that is won't be valid in the electrostatics. That's why charges should be rest. Charges should be rest means when it will be at rest, it should not experience any electric, means it should not experience any force. It should not experience any force means it should not be present in the electric field. So electric field should be 0. Electric field should be 0 in the sense what should be 0? Q should be 0. So Q should be 0 in the sense whatever the charge we provided for the sphere, that charges should be what? Distribute over the surface in order to maintain electric field intensity inside 0. That's why what will happen in the case of conducting bodies means if a charge is provided to it, so inside the conducting body electric field intensity is 0. So this happens when charge is 0. So where charge will be resides means when a charge is provided, the entire charge will be resides over the surface. Entire charge will be resides over the surface only. Inside the body the charge is 0. This happens in what type of body? Means a conducting body. Examples are metals. Next one, non-conducting body. What is a non-conducting body in the sense? Suppose if you see non-conducting body, if you are taken, So example of non-conducting body means the body which does not allow to move freely the charged particles. So that kind of body is non-conducting, like insulators. Insulators in the sense dielectric mediums like glass, ceramic, non-metallic bodies like plastic and all, those we can call it as a non-conducting bodies, non-metals. In these, the charged particle will not move freely as you seen in the case of conducting bodies. Now charged particles, even if it is there, they won't be move at all. Even the charged particle is present inside, they will produce the electric field. So even this electric field is exert a force over it, but that force will not move the particle. That's why these charged particles will not move in the sense there is no movement of the charged particles in the sense what we discussed electrostatics, that is charged particle should be at rest, is valid. So in the case of non-conducting, what will happen means the charge will be reside inside as well as on the surface. Throughout the body charge is distributed means then we can say that is a non-conducting body. So this is the thing, but in conducting body charges freely move. That's why what will happen, they will be starts moving when electric field is present inside it, then that is it is not valid of electrostatics. So that's why in non-conducting even the electric field is there inside, so it not tends to move the charged particles. Why? Because in non-conducting body charged particles cannot move freely. That's why inside and as well as on the surface also charge will be present in the case of non-conducting body. So remember it, conducting body charge will be present over the surface only, non-conducting body over the surface as well as inside the surface also be charge will be present. So this point you remember it. Then we will go to the next application, that is what we discussed, that is electric field intensity due to infinite charged conducting cylinder. Especially we are mentioning the sentence that conducting cylinder, non-conducting cylinder. So conducting cylinder time the electric field intensity cases are different, non-conducting time the cases are different here. So that's why you observe clearly whether it is conducting or non-conducting body. Now I am going to continue that is electric field intensity, electric field intensity due to non-conducting. First I will discuss the conducting infinite charged cylinder, infinite charged conducting cylinder. Now we will go to that term. I am taking a cylinder whose charge density is sigma, because we have different kind of charge densities, linear charge density, volume charge density, surface charge density. If the charge is distributed over the surface means surface charge density. If the volume charge is distributed over the line means along the lengthwise means linear charge density. The charge is distributed throughout the body means volume charge density will take it. Here what kind of body? Conducting body. Conducting body means charge will be distributed over the surface only. That's why we will take here surface charge density sigma. Now, and it is an infinite charged cylinder. This is the cylinder having infinite length and the charge is given to it. So charge will be resides over the surface only, whose radius is capital R. From the axis, this is the center to axis, from here to radius is R. Now you can understand that what are the steps we are following to determine the electric field intensity due to this charged cylinder. At a distance R means one point will take it as outside of the cylinder, what is the electric field intensity. On the surface of cylinder, what is the electric field intensity. Inside the cylinder, what is the electric field intensity, that we will be discussing it. So what is the surface charge density of it is sigma, that is we can take it surface charge density is sigma. Now I am taking a point, first one, I want to find the electric field intensity from the axis of the cylinder at a distance r. So this is a point P. Here electric field intensity is how much? We need to be determine it. Here electric field intensity is how much? If you want to determine it, what steps we followed? So we should first construct one imaginary Gaussian surface. What kind of surface here we can choose is, so this cylinder should enclose means we have to imagine another cylinder whose radius is smaller. So we will consider one imaginary Gaussian cylinder. Shape of this surface is cylinder because we enclose it, whose radius is smaller. Here you see capital R is the radius of the cylinder and smaller is the Gaussian surface radius. Now I am taking that one cylinder whose length is L as well as the radius is R. Such kind of Gaussian surface I am going to be imagine. Now constructing like that. This is the Gaussian surface whose length is L, whose length is L and radius is R. Then what will happen? Due to this cylinder, the electric field intensity is radially in all the directions, radially outwards. So electric field will be radially outwards in all the directions. This electric field intensity is E. Because at the same distance R, electric field intensity at every point is magnitude wise remains same. That's why electric field intensity at every point is same only, and it is the direction is radially outwards. Then we want to find the electric field intensity at a point P here. So to find this, first step we followed, we constructed one Gaussian surface whose length is L as well as radius is smaller. Now if you want to find the electric field intensity at this point, what is the next step here? We have to consider a small area. Now I am going to take here a small area of this Gaussian surface. This is a small area of this Gaussian surface whose radius surface area is ds, and electric field intensity at this point, electric field intensity E as well as the radius vector, both are along the same direction. Then the theta, angle between the electric field intensity and area vector is 0. Now we are going to be applying the Gauss law for it. Now what is the Gauss law? We know mathematically integral E bar dot ds is equals to integral E bar dot ds bar equal to 1 by epsilon naught times the net charge enclosed. Here dot, but the angle between electric field intensity and area vector is 0, so we can write E ds cos 0, that is equal to 1 by epsilon naught times the q net. Then we will write this as E, because E is we are taking outside of the integration. The reason is the E remains constant at any point over the Gaussian surface. And now we are going to take that E outside and cos 0 is 1, integral ds. What about the integral ds? Integral ds is nothing but, you observe here, the ds is a small surface area over the Gaussian surface. Integral ds means the complete Gaussian cylinder area. Complete Gaussian cylinder area means that is nothing but we can write as integral ds is nothing but integral ds is Gaussian surface area. That is Gaussian surface area means the cylindrical surface area is perimeter 2 pi r, radius of the Gaussian surface, and the length is L. So 2 pi r into L. So integral ds place we can write like that. And what about the charge enclosed? So charge enclosed is nothing but, we have to be understand that charge enclosed means this Gaussian surface, how much charge it is enclosed, that we need to be take it. This Gaussian surface, how much charge enclosed in the sense, this is the charged body. Okay, so surface charge density into charge means net charge enclosed by the body means we have discussed that in linear conductor time, linear charge density into length. In surface charge density case, surface charge density into area of the body. So of length L. So area of the body means this is the area we need to multiply with the surface charge density. Then we know what is the charge enclosed by this Gaussian surface. So charge density into this particular cylindrical area means that is 2 pi r into length L. So net charge enclosed here is, we can write that here integral ds means the area of the Gaussian surface 2 pi rl, as well as net charge enclosed means the charge enclosed by the Gaussian surface, that is what surface charge density into area of this part that is 2 pi r into L. Now if you substitute these things in this expression, you can write that, see, E we are taken outside, integral ds means 2 pi rl, that is equal to q net in the sense 1 by epsilon naught times c. Q net means sigma into 2 pi capital R into L. Then we can cancel the L as well as 2 pi on the both sides. Then we have electric field intensity E equal to sigma R by epsilon naught small r. So this is the electric field intensity. This is the electric field intensity what outside a distance r. So E, electric field intensity outside is inversely proportional to the distance, and electric field intensity outside is sigma r, where capital R is radius of the cylinder and as well as the smaller is nothing but distance where we are want to find the electric field intensity. So this is the things you can understand well. Next, if you are taken on the surface, so where we first discussed it, this is outside of cylinder. So another case, on the surface is how much? Next, inside the cylinder is how much we will be discussing. On the surface means, if you observe, on the surface in the sense the Gaussian surface should be over the, means the Gaussian surface radius and what the cylindrical radius should be same. So Gaussian surface radius smaller equivalent to capital R means that is the point lies on the surface of the cylinder. Now we are going to discuss that. So inside is on the surface is how much? Outside is sigma capital R by epsilon naught small r. If small r equal to capital R, that is nothing but the Gaussian surface is over the cylinder. Okay. Then if you want to find the electric field intensity on the surface of this cylinder means just we need to be write small r equal to capital R. That is enough. Now I am going to write that here. Second one, on the surface of cylinder, on the surface of cylinder if you taken just small r equal to capital R means, so that is we were taking on the surface. Then how this expression is going to be changed? E on the surface means in this expression smaller place even I am writing the capital R, then sigma r by epsilon naught capital R, then it is sigma by epsilon naught. This is what electric field intensity on the surface of the cylinder. As well as inside we are going to take it now, the third case. So this is, you observe it here, it is not any depends on distance. So we can say it is constant. It is maximum value. Now the third case, what is the third case here is What is electric field intensity inside it? See what kind of body we are taken here, that is nothing but conducting body. And already we discussed whether the charge is present inside the conducting body or not. So in case of non-conducting body, charge will be present inside as well as over the surface. But in case of conducting body, inside the body the charge is 0. So inside the body charge is 0 means obviously you can understand electric field intensity is also be 0. So let us see that third one. So inside the cylinder, if inside the cylinder if you are taken, so you observe inside the cylinder is charge inside is 0. Charge inside is 0 in the sense, according to Gauss law, E integral ds is equals to 1 by epsilon naught times the net charge enclosed. So if you are taken the Gaussian surface inside, so out inside point in the sense I am going to take the Gaussian surface where now? Inside of it. This is the Gaussian surface. Suppose the point you are going to take inside now. Here somewhere you are going to take it. The point P. Now only this much radius of what cylinder you need to be construct, imaginary Gaussian surface you need to be construct of radius R. So whose radius small r is less than capital R now. So small r is less than capital R now. Now I am constructing this much of Gaussian surface like this. Now you observe, earlier the Gaussian surface was present outside, that's why it enclosed some charge. But when you are finding the electric field inside it, the Gaussian surface is inside the cylinder. So the Gaussian surface inside the cylinder means inside charge is 0. So Gaussian surface does not encloses any charge. So net charge means what we discussed, net charge means the charge enclosed by the Gaussian surface. But inside point the Gaussian surface is inside the cylinder. So inside the cylinder no charge is present. So net charge enclosed by the Gaussian surface is 0. Then what will happen here? Right hand side Q net is 0 in the sense this will be 0. Then electric field intensity E equal to 0. So inside the conducting cylinder electric field intensity 0. So whatever the body shape you take it, whether it is cylinder or sphere or anything, so conducting body means inside what will happen means electric field intensity will be 0. Non-conducting case electric field intensity present. The reason I told you already, that is charge will not be reside for the conducting bodies inside the body. It is always resides over the surface only. That's why here inside point case the electric field intensity is 0. So graphically we have to represent this electric field intensity, so with respect to distance from the axis of the cylinder. So that variation of graph how can we draw here is, let us see that first I am going to write that outside of the cylinder, outside of the cylinder E electric field intensity is sigma capital R by epsilon naught small r. So E outside is inversely proportional to R. Next, on the surface means what will happen? You wrote small r plus capital R. Then how the expression is going to be changed here? E on the surface is sigma by epsilon naught. Next, here inside the surface means electric field intensity is 0 we taken. So E inside is is 0. Now if you are going to be represent this in a graphical way, so that is variation of electric field intensity with distance from the axis. The variation of electric field intensity with distance from axis of cylinder. Then if you are taken that graph like this, so on y-axis electric field intensity and on x-axis distance from the axis if you taken. Now let us observe outside center, from center to surface electric field intensity is 0. So this is origin and this is a point where small r equal to capital R means this is surface. Up to this extent that is nothing but comes under inside region. Inside region electric field intensity 0. That's why here we no need to be represent any graph like this. But exactly over the surface, what is the electric field intensity? Exactly over the surface means at this point electric field intensity value is sigma by epsilon naught. This is the maximum value. So this is sigma by epsilon naught. It is the maximum value that is takes place what? At the surface. And inside here electric field intensity is 0. This region comes under inside. Next, outside if you observe, what is outside? You are observing that electric field intensity is inversely proportional to the distance r. So both are inversely proportional to each other means the nature of the graph is a rectangular hyperbola. So the nature of the graph is rectangular hyperbola. So from outside of this cylinder, if you draw the graph, this is a rectangular hyperbola, that is E is inversely proportional to R. So this is the variation of electric field intensity of infinite charged conducting cylinder. Okay, so here conducting cylinder. So if non-conducting case, how it will be there in the sense inside the charge will be present. So inside charge is present means understand inside electric field intensity not be 0. Inside some electric field intensity will be takes place. Then that case we will be discussed in the next class.